In the graph number 3, there is the effect of ammonia concentration versus terminal layer thickness. In heterogeneous equilibria, such as in chemical solution deposition, where solidification from the saturated solution takes place, the control over equilibrium constant, that is solubility product, plays an important role. In our case, equilibrium was established in a bit different fashion. TA 0.3 ml optimized forms ZnTA complex. Hydrogen hydrate was kept at its arbitrary value 9 ml, and ammonia was varied from 10 ml to 25 ml, and the films were obtained. Ammonia liberates additional OH ions, thus providing more stability to the metal ion complex formed in the solution bulk, that enhances the film adherence to the glass substrate and may cause increases in layer thickness. The resulting pH of the reaction bath was 10 plus or minus 0.2. Thus, with the addition of TA and ammonia, two processes initiates simultaneously. First process is the complexation of Zn2 plus ions by TA, and second process is control of pH of the solution bath around the desired value, that helps to enhance the rate of formation of a thin film layer, and consequently the layer thickness bit increased. Therefore, role of ammonia in our case is to improve the layer sticking on the glass substrate. The addition of OH ions with further increases in ammonia helps to make the Zn2 plus TA complex more and more stable, that keeps the metal ions well arrested in the complex, thus decreasing the rate of release of metal ion species significantly, and hence the layer thickness decreased. In the last graph, that is graph number 4, there is the effect of hydrogen hydrate on terminal layer thickness. Hydrogen hydrate N2H4 has found to have a variety of applications in many industrial, agricultural and other fields, including farming and anti-corrosive agents, synthetic resins, rubber additives, etc. It has also been used as a medium to precipitate 1 and 2 row transition metal sulfides and selenides. Hydrogen hydrate has 2 free lone pairs of electrons and 4 substitutable H atoms. The presence of lone electrons pairs allows hydrogen hydrate to coordinate to a metal ion either as a unidated or bridged bidentate ligands to form complex in the aqueous solution of the metal salts. Further, hydrogen hydrate is an excellent reducing agent, since it tends not to coordinate strongly with the metal ions, and therefore it is relatively easy to dissociate hydrogen hydrate from the precursors at relatively low temperature. In our case, the hydrogen hydrate concentration in the reaction bath was therefore varied from 4 ml to 10 ml, and films were observed under the optimized condition of different parameters. So optimized hydrogen hydrate was 6 ml. So in case of thickness variation with compositions, we observe that the terminal layer thickness is found to be increased with increases in x up to 0.075 and then decreased for further higher values of x. So the influence of CO2 plus concentration addition on the film growth was examined for whole range of the sample 0 less than or equal to x less than or equal to 0.275. The terminal layer thickness was measured for each of the sample. For x is equal to 0, the layer thickness corresponds to the thickness of pure ZnSe and is 1070.8 nanometer. The terminal layer thickness is found to be increased with increase in x up to 0.075 and then decreased for further higher values of x. The measured thickness the increases in thickness can be attributed to the enhanced rate of nucleation by the addition of CO2 plus up to x is equal to 0.075 and a considerable scattering may cause the observed decreases in layer thickness at higher x values as shown in the figure or as shown in the graph, and this is published in the international journal in material science semiconductor processing. So another physical parameter of surface wettability was studied. In this case, the contact angle measurement is a surface thermodynamic evaluation and is the angle made by the tangent to the liquid vapor interface drawn at the contact line that makes an angle with the solid surface. Weighting property of the ZnSe and Zn1 minus x COX SE films was tensed by measuring the static and dynamic water angle by a tensile drop method. To evaluate weighting behavior of the films, images of the contact angle theta of water droplet on films of different compositions x were measured and are shown in the figure. It is clear that droplets are nearly spherical in shape and found to be stable for several minutes. The contact angles were therefore measured for all the samples, and it has been seen that increases in CO2 plus contact in ZnSe host increased the contact angle from 93 degree to 160 degree as CO2 plus content was varied from 0 to 0.275. This shows that the growth of ZnSe and ZnCoSe films on the glass surface is hydrophobic in nature and can be attributed to the high surface energy and microstructural amendment in the deposited films. Again, from the table we can see that there is some physical observations on ZnSe and ZnCoSe thin films. The terminal layer thickness in nanometer decreases from 1070.8 nanometer to 793.7 nanometer with respect to composition parameter 0 to 0.275, and angle of contact was increases as the composition parameter x were increases. We also observe change in physical color appearance with CO addition. Both ZnSC and ZnCoSe thin films were thin, uniform, smooth, diffusely reflecting, and tightly adherent to the substrate support. As grown films showed change in color from ash gray to charcoal black as shown in the figure. As a result of CO2 plus addition into ZnSC host lattice. The color variation studies are further supported by colorimetric studies as the CO2 plus incorporation in ZnSC is increased, the lightness changes from brightest white to the darkest black. The red apparent colors are of negative values while green opponent colors are of positive values. So the composition in as grown thin films was studied with the help of EDS, and these are the EDS spectrographs of ZnSC and ZnCoSe thin films. So from the EDS studies, it is observed that the pure ZnSC films are rich in Zn2 plus, and the addition of CO replaced Zn from the ZnSC lattice, whereas Se2 minus content remained almost the same. We have also used XPS for the composition analysis. We have studied the chemical state of Zn, CO and Se by deconvoluting the surface spectra on separate elements using the model XPS Fiji MATLAB 2000 thermoscientific UK. The excitation source ALK alpha radiation H nu is equal to 1486.74 electron volt using the constant analyzer energy of 10 electron volt. In the figure shows the typical XPS surface spectra for Zn1 minus X COX SE, that is 0 less than or equal to X less than or equal to 0.275 thin films. So from the Zn2P core levels, it is observed that the XPS spectra being deconvoluted on Zn showed Zn2P 3 by 2 and Zn2P 1 by 2 energy levels appearing due to the spin orbital splitting and shake-up satellite. The second observation is that the observed chemical binding energy shift between Zn2P 3 by 2 and Zn2P 1 by 2 is comparable with that of pure Zn metal, which indicates that the Zn ions are preferred in the +2 oxidation state. Zn2P splitting nearly equal to 23.12 electron volt and shake-up satellite in core level confirmed the chemical state of Zn elements as Zn2 plus. Again, this figure or this XPS data published in the journal Material Science Semiconductor Processing. In case of cobalt 2p level, it is observed that in the as grown Zn1 minus X COX SE thin films, because of the strong spin orbit coupling, the CO2p peak splits into CO2p 3 by 2 and CO2p 1 by 2 with the separation of nearly equal to 15.88 electron volt, and this is in close consonance with the standard separation of 15.05 electron volt corresponding to CO2 plus. Again, this data published in Material Science Semiconductor Processing. So in case of SE3D core levels, it is observed that narrow scan of SE3D core level indicated the presence of Se2 minus chemical state at 54.15 electron volt with a little shift on higher binding energy side. The binding energy of Se element in the range of 54.15 electron volt is in close consonance with the standard value of Se2 minus chemical state. This is the tabular form of XPS measurements, as we can see in the table number 1, and in the second table there is the values from EDS and XPS measurements. They roughly matches. Further, XRD was used for the structural analysis. 2 theta range from 20 degree to 80 degree. In this XPS measurement, there is the interplanar distance d, intensities of reflection, that is I by I max, lattice parameters A and C, crystal size, microstrain, stress, dislocation density, and the number of crystallites were calculated. From XRD studies, we noted that both ZnSe and ZnCoSe films are structurally cubic, while the range 0.1 is less than or equal to x less than or equal to 0.275. The films are composites of different faces. ZnSe, the face of ZnSe is cubic and the face of CoSe is hexagonal. So in the XRD study, we have observed two faces of and the two structure, that is first structure is the cubic and the second structure is the hexagonal structure. The observed intensities of reflections, d values, and the lattice parameters have good consonance with the JCPDS cards. The value 2 theta for the 111 dominant reflection shift appreciably towards higher 2 theta side up to x is equal to 0.0275, and for the value of x greater than 0.075 a left shift in 2 theta has been observed. The above results can be understood as the cobalt integrates considerably into ZnSe host lattice. So this is the table for characteristics properties of ZnSe and ZnCoSe thin film. ZnSe and ZnCoSe thin films as determined from XRD studies. There is the different parameters varies with composition parameters. Different parameters are like average crystallite size in nanometer, grain size from FESM we study in the next slide, microstrain, dislocation density, and the number of crystallites. So the Perkin-Elmer spectrometer was used for FTIR analysis. The bands at 746 centimeter inverse 757 centimeter inverse, frequencies corresponding to the stretching and bending vibrations of the ZnSe bond due to the adsorption of Zn and Se. The peaks observed at 2842 centimeter inverse to 2885 centimeter inverse and 2918 centimeter inverse to 2930 centimeter inverse are the bending characteristics vibrations of Zn and ZnSe in the ZnSe thin films. So this is the assignment of the bands for ZnSe and ZnCoSe samples from the FTIR studies. We also have used the field emission scanning microscopy, that is FESEM, for micrological studies. FESEM micrographs revealed transformation of microstructure from spherical globule type to a mixture of spherical globule and spindle type elongated structures of uneven shapes and sizes. The fewer ZnSe and Zn1-X COX SE in the range of 0 less than or equal to x less than or equal to 0.01 samples are composed of almost spherical shaped crystallites significantly reduced in size. For the samples in the range of 0.025 is less than or equal to x less than or equal to 0.075 range, the spindle shaped growth results, which appears to be homogeneous, composed of the crystallites of different irregular sizes and shapes, indicating the possibility of the solid solution formation. So surface micrographs of the samples in the range of 0.1 less than or equal to x less than or equal to 0.275 showed a mixed composite type structure of both spherical ZnSe and elongated threaded type CoSe, and this data is published in the journal Material Letters. The atomic force microscopy, that is AFM, was also used for topographical studies. The surface topographs consist of the hillocks and valleys, suggesting the crystalline nature. With increases in CO2 plus content in the film, the surface topography tends to be rough and the crystallites tends to be rounded, flatty hillocks, maintaining more or less same structure for very low concentration of CO in ZnSe, that is in the range of 0.005 to 0.01, and as CO went on increasing, again the crystalline growth results, thereby increasing the average and RMS roughnesses. The further observation is that the increases in X collapsing of the crystallites occur, reducing the roughnesses. In this table, we have shown some material parameters for ZnSe and Zn1-X COX SE in the range of 0 less than or equal to x less than or equal to 0.275 thin films as evidenced from AFM studies. The magnetic mapping of surface topography was done with the help of MFM, that is the magnetic force microscopy. The magnetic, it is from these pictures it is observed that the magnetic clusters mimicking the topographic features and magnetic aggregates of irregular shapes. The color constant with the aggregates suggest existence of dissimilar magnetic domains and the presence of mono and multi magnetic clusters. And this MFM study data published in the Material Later journal. As deposited thin films were characterized by optical studies, the optical transformation spectra were obtained in the range of wavelength from 200 nanometer to 1200 nanometer. The absorption coefficient alpha is nearly equal to 10⁴ centimeter inverse, and a systematic increases in alpha was found due to the creation of localized states within the band gap. From the alpha values, we have plotted graphs of AH nu square versus H nu for band gap determination. The plots shows the band gap of various compositions. The EG band gap energy decreased from 2.71 electron volt to 1.96 electron volt with increased CO2 plus content into SE framework. The optical transformation are of the band to band direct type with a transmission index of around 0.5, and this data is published in Journal of Material Science, Materials in Electronics. Here are some optical characteristics of the ZnSe and ZnCoSe thin films. These optical parameters varies with composition parameter X. The optical parameters are like band gap energy, power factor M, EA, excitation coefficient, refractive index, dielectric constant. These dielectric constants are like real dielectric constant, imaginary dielectric constant, static dielectric constant, high frequency dielectric constant, and the last, electron effective mass. Again, this table published in the Journal of Material Science, Materials in Electronics. Electrical transport studies were done in the range of 300 Kelvin to 515 Kelvin. Increases in conductivity with increases in temperature confirmed erroneous behavior of the films. The two distinct conduction mechanisms are found. The first one is the grain boundary scattering in the higher temperature region, and in the lower temperature region there is the variable range hooping. From variation of electrical conductivity with composition, we noted that conduction is affected by the grain boundaries associated with the material. The mechanism is attributed to the thermal excitations of the charge carriers across the potential barrier at grain boundaries. The electrical conductivity increased with composition parameter X continuously as CO2 plus concentration in the films. When CO content in the bath was increased with film content, CO also increased as CO2 plus is more metallic than Zn2 plus, and increases in the electrical conductivity is obvious. And this data is published in the Journal of Material Science, Materials in Electronics. The type of semiconductor was determined by using thermoelectric power, and from this data it is seen that the conduction by the sample is found to be the N type. The TEP increased with temperature, confirming major contribution from the electrons to the conductivity and degenerating nature of the deposited thin films. TEP decreases with increases in composition parameter X. With increases in temperature, both carrier concentration and the mobility are found to be increased, and this variation is observed from these graphs. In the first graph, there is the carrier concentration variation with composition parameter, and in the second graph, it is observed that there is the variation of mobility with composition parameter X. As the composition parameter is increased, the carrier mobility and the carrier concentration is found to be decreased. This also explains increased electrical conductivity with increased composition parameter X. Dependence of mobility on temperature suggested possibility of scattering mechanism with the intergrain barrier potential. The straight line plots of log mu t raised to 1/2 versus 1000 divided by t indicated the presence of grain boundary scattering limited conduction mechanism. The grain boundary potential phi b decreases with increases in X. These are the electrical characteristics of the ZnSc and ZnCoSe thin films, and these characteristics are varies with composition parameter X, and the characteristics are activation energy, that is high temperature, low temperature, conductivity, ED, barrier potential, carrier mobility, and the last one is the carrier concentration. As application part, we have decided to form EPV devices. We have designed electrochemical photovoltaic device as shown in the figure. Homemade glass cavite cell consisting of two glass test tubes assembled in a H shape. A window of 1 centimeter square was made for illumination of the electrode material. A fabrication of photovoltaic cell of the configuration is like this: Zn1 minus x COX SE oblique NH4Cl oblique C. To being with electrophotovoltaic studies, we have chosen suitable electrolyte. First, VPH and IPH were measured by changing the electrolyte concentration, and the various electrolytes are tested like potassium chloride KCl, dimethyl sulfoxide DMSO4, hydroquinone, ammonium chloride NH4Cl, DMSO 1 mole plus NH4Cl 0.5 mole, potassium hydroxide KCl plus S plus Na2S, likewise etc. But there is the electrode dissolution in the some electrolytes like sulfuric acid, ferricyanide, iodide, polyiodide, sulfide, polysulfide. From this table, it is found that the 0.5 mole NH4Cl electrolyte offers a relatively better match both for ZnSe and ZnCoSe electrode material. In the electrical properties, the IV characteristics in dark at 303 Kelvin were studied. The polarity of dark voltage was negative towards the semiconductor electrode. The IV curves are asymmetrical, suggested a rectifying nature of the electrode-electrolyte interface. The junction ideality factor were then determined from the plots of log I versus V. The higher values of ideality factor suggested the dominance of series resistance as well as the structural imperfections induced by CO into ZnSe. Smaller ideality factor for X is equal to 0.075 suggested lower trap density at electrode-electrolyte interface. CV measurement on a junction was also studied. The CV measurement on the junction provides useful information like flat band potential, donor density, band bending, position of the band edges. The space charge layer capacitance was measured under reverse biased condition. Plots diverge from linearity, indicating the graded type nature of the junctions. This behavior is attributed to the existence of surface states at the interface that decreases the electrochemical performance, and the flat band potential gives the relative position of Fermi level in the photoelectrode as well as in the electrolyte. The negative sign of flat band potential indicates n-type nature of the material, that is ZnSe and ZnCoSe. Flat band potential increased up to X is equal to 0.075 and then decreases with increases in X. The built-in potential phi b were determined by measuring the reverse saturation current in temperature range from 308 Kelvin to 363 Kelvin. The reverse saturation currents exhibits an almost exponential variation with temperature. The plots tends to be non-linear at high temperature and can be attributed to the full Frankel type conduction mechanism. The barrier height is maximum for the PV cell with electrode composition of X is equal to 0.075. Again, this is the photoresonance studies under illumination of 5 to 50 milliwatt per centimeter square. A plot of VPH versus LNPH, LNIPH should therefore yield a straight line, the shape of which gives the junction identity factor NL in light. Again, this plot shows the short circuit current IC was measured as a function of the incident wavelength 400 nanometer to 900 nanometer to stay the spherical response. The ZnCoSe material is spectrally less sensitive within the range of wavelength studied. The rise and decay of VOC with time are studied for the speed response studies, and this plot shows the slow rise and slow decay as a consequence of large concentration of surface states at the interface, and the input intensity of 13.4 milliwatt per centimeter square was used for power output characteristics. IV characteristics shifts in fourth quadrant. From the power output curve, it is seen that VOC and ISC has a maximum value of 429 millivolt and 154 microampere per centimeter square respectively for X is equal to 0.075. The fill factor and efficiency are found to be enhanced from 0.21% to 0.29% and 0.84% to 1.44% for a PV cell of electrode composition equal to 0.075. And this is the performance indicator of the electrochemical PV cells of a different photoelectrode composition X, and it is found that the 0.075 photoelectrode offers a relatively better than others. And finally, these are the remarks or the conclusions. Thus, analysis of the electrochemical PV cell properties showed the PV performance is not encouraging at the present moment. The performance is below the expectation, and we attribute this low performance to the low density polycrystalline film morphology, which causes high concentration of the lattice and boundary defects. The low shunt resistance, which is a direct consequence of the micropores present in the films, and the absence of the post deposition treatments, and the reflection of the light from the photoelectrode surface. The next point is the small electron affinity difference between the materials. And the last one, instead appropriate window layer and formation of multi-junctions are required provides as device performance of the material should be improved. Thank you and thank you.